Hey, okay, cool. So I'm going to talk about this slightly scary sounding paper, but I hope I can convince you it's like actually some really nice, elegant ideas that are pretty quick to kind of get your head around once you try. So a bit about me first. I'm Tim Ruffles, currently an engineer, product engineer at Poolside AI. We're a foundation model company, so building models from pre-training all the way through post-training, not just kind of fine-tuning other people's models. And aside from that, building coding assistants like you probably use already, a bit like Cursor, Klein, all that kind of stuff. We're also hiring. Center of mass in terms of engineering is in Europe, which I think is unusual for labs that are hoping to get to the frontier. We're remote. We have monthly meetups in Paris, which is like a nice balance. At least for me, I really enjoy it. And I've had a great time. I've been there for a year and a half and recommend it. Before that, I was at Plaid. It's a fintech, power stuff like Venmo, and I was one of the original engineers on GitHub Actions at GitHub. Sorry about the YAML. We really tried. I really fought hard, but couldn't win that battle. So this paper, someone was saying, always be suspicious when someone puts entropy in a paper. They're just trying to sound, smart, complicated. I think that's spot on. This is just a gossip protocol, and a gossip protocol is a really nice named protocol. So we've got a distributed system, and just like people, the nodes are going to gossip with each other, and it's completely decentralized. We're just going to share news, and that's going to propagate the information way faster than you'd think, and actually pretty reliably. So we talk about this kind of like the two algorithms. The paper is about anti-entropy gossip protocols, and the idea here is that we have total information is very high when everyone thinks different things, and the information will drop as everyone agrees on the same stuff. It's almost like, there's less information. If you were going to compress everyone's information, a lot less difference, right? So we're bringing the information level down, the entropy level down. And we do that with reconciliation we're going to talk about. And it's in contrast to another kind of category of gossip protocols called rumor mongering, which is more like when you hear a rumor, you pass it on, and you don't care so much about what everyone else knows yet. So you're just kind of assuming that this is new to other people, but you don't know for sure. And the distinction is there's no reconciliation between the two. So you don't kind of chat and get a sense of what the other person knows. You just sling rumors at them. That sounds probably like a little loosey-goosey, and it is. That's just like a kind of probabilistic convergence. So it may never converge. It's just high probability it will. Whereas anti-entropy should theoretically always converge because of the reconciliation. Yeah, it's going to kind of like self-heal over time. Oops, sorry. And why are they interesting, gossip protocols? Like, why would you use one? What kind of system would you use it for? What are the properties that make it cool? So I've already mentioned the first one, peer-to-peer, right? There is no central node. It's very different from, like a database with like a leader, where if it goes down, you have a single point of failure. You have to do like a leadership election, all this complicated stuff. It's pure peer-to-peer, no control nodes, no control plane. Everyone's the same. Therefore, it's very robust. You can lose half the nodes. Half the nodes can get kind of partitioned from everyone else. Nothing changes. It's all working exactly as before. When they get reconnected, self-heals, everything's great. The anti-entropy thing is the self-healing part. So rumor mongering, if you lose updates, you lose gossip, you're never going to get them again. Whereas with the reconciliation from anti-entropy, we're going to see it can self-heal. The node can go offline, come online, all that kind of stuff, and things will be good. And then the cool thing is the expected propagation is logarithmic. Or to put this backwards, the inverse, the propagation speed is exponential. And looking in the history of these algorithms, the other kind of name for them is epidemic protocols. And you can use the same modeling techniques to model the propagation speed of gossip protocols as you use for modeling like epidemic spread. So if you remember like the R number that we all probably heard about during COVID, you can model how fast you're going to get your information out using those analysis techniques, which is kind of intriguing. Can't all be good though. Like there's got to be some weaknesses, and there's a major one, which is they're eventually consistent. There's absolutely no consistency guarantee here at all. So there's no causal ordering. You're not going to be able to say that just because this happened at time 0, you're going to hear about it before something happened at time 100. There's no guarantees at all. All bets are off. So that's the kind of power of like gossip protocols. Very robust, very self-healing, all sorts of good stuff. However, what about this paper? Like, why are we talking about this paper in particular? It didn't invent gossip protocols for sure. They're like very, very old. I think one of the first papers was written when I was born, 1987, so a depressingly long time ago. And probably before, by the way. I don't think I've done all of the research on how old they are. But this paper, the authors, if you have a look, are a very interesting group of people because they were around the kind of early days of AWS. And so it turns out gossip is very ubiquitous in many of the systems that we've all been relying on today for many, many different things, whether we're using apps or, in our own software. So like DynamoDB uses gossip famously, S3 apparently does. And this top one, Astrolabe, which I've never heard of before, is more of an internal thing in Amazon. And if you look at the authors on Astrolabe, so one of them is, of course, one of the co-authors of the paper, there's also this Vogels guy. Who's Vogels? Anyone know who W. Vogels is?
CTO.
Yeah, right. So like, knows a bit of one or two things about distributed computing. It's very interesting that this paper, the team behind it. Secondly, and I probably should have given a trigger warning for this for anyone from Monzo, because I've heard from people who work here, this is maybe not their favorite thing. Some people really like it. Is Cassandra, which is a database that has many of the properties that I mentioned earlier about gossip protocols, peer-to-peer, no single point of failure, very robust, et cetera, et cetera. And it turns out that it uses gossip protocols. Which gossip protocol? Turns out it's this paper again. And you can see it's calling it Scuttlebutt. And that is the name of the reconciliation algorithm this paper puts forward. So Scuttlebutt, it just turns out, is another word for gossip. Comes from sailors back in the day, apparently, where they had a big water bottle, water jug on the deck, and they'd stand around it and gossip, right, like a water cooler. I found out from reading about Captain Cook lately, this was probably also spiked with rum, because otherwise your water on a long trip would go like all algae and gross. So this is also like, probably a good time. It's more like being at the pub. And how did I come across it? Like, I've never used gossip protocols in production myself. I actually just came across it 10 years back at a bunch of JavaScript conferences where people were using a weird and wonderful distributed social network based on secure Scuttlebutt called Patchwork, written among other people by this guy, Dominic Tarr, who's like a mad New Zealander who lives on a boat. And this thing is like zombie apocalypse social networking. So it's distributed peer-to-peer, fully encrypted, offline native, all this kind of cool stuff. And it's based on this paper as well. So that's how I kind of came across it. Thought, wow, this is based on a real actual paper, read it, and ever since I've kind of seen one of my faves. Cool. So I told you that the team is interesting. It's obviously influenced other people, but why? What did the paper do? The big thing is, although I've told you that there's an expected logarithmic propagation speed, as with so many things in life, your expected and your actual time can be very different. And so what the authors noticed was that with the existing gossip protocols, you'd end up with everything just spending its time gossiping and not getting any forward progress. So that's the cost in kind of CPU and bandwidth of just getting the gossip propagated was overwhelming everything else. Your nodes were stuck, your database, was not converging. So the existing approaches were like maybe too academic, forgot that CPU and bandwidth were like a thing, according to this paper, and they just didn't handle this well. You can see the previous papers thought this was a tiny and unimportant detail, but they were like, no, CPU and bandwidth, that's what we live and breathe at AWS, and this is what we're going to worry about. So this paper, we're going to first off introduce the nuts and bolts of gossip protocols. I'll talk about the status quo that they kind of set up as a straw man, like that's not good enough. We'll then talk about Scuttlebutt, the hero of our paper, this new reconciliation algorithm. We'll talk about flow control, so how we can decide how fast to send updates, again, without any central point of failure. And we'll talk about some kind of empirical experiments that the authors run, and I've tried to reproduce that kind of show you how well these algorithms actually work in practice. Cool. Okay, so hopefully, actually, yeah, hands up, like, who read the paper? Oh, a few people, amazing. Who like even glanced at it before they came? Okay, cool. So like, I'm gonna go through section by section and hopefully give you like placeholders you can go and like have a look at the paper if you haven't, or if you do, just to kind of situate you in the paper you've read. And I mostly use code rather than maths. I at least personally find it much easier to read, and I kind of decode the math into code as we go. So like I said, we've got a bunch of nodes. They're going to gossip at a set frequency. It's one of the parameters we're going to say. And that's basically just talk to another node at random, send them some hopefully interesting information, and then they'll update themselves because it's anti-entropy. They will reconcile with the news that the data they have already. They'll try and make forward progress. The reconciliation's defining how we do that. So the state that we're replicating is very simple as it gets. It's a dictionary, keys to values, but the values are versioned. So you can see we've got key, value, and a version number, which the paper calls n. So we've got key, v, n. Values, we'll talk about in a sec, but the version numbers are the important bit for pretty much all of this discussion. In the code, I'm going to assume these are like named tuples, so I can do like .v to talk about them. Versions, infinite set, whatever you like, I would suggest, integers like in the paper. There's no global ordering. That's a really important thing to remember. Like I was saying, there's no global consistency guarantees at all. So the version numbers only make sense for a single participant. The value, according to the paper, is unimportant, right? So whatever you like. And we'll see this comes up a couple of times when we talk about it. So we can basically forget about values. Kind of weird, but they can be whatever you like. It doesn't matter. Okay, that would be a very uninteresting algorithm, but we need to talk about everyone else's data, right? We're replicating. The paper calls a single node's state sigma, and it calls the view on everyone else's state mu. And that's just another level of the dictionary. So now we're going to have a participant ID, and then inside we have our version of their state dictionary. That's what we're replicating. So we're going to try and keep this up to date. And you can see it also has the key value version. So we've got the values and the versions. Nice. Putting this back into the notation, that's hopefully you can see that it's just a dictionary, even though it has lots of fancy Greek bits and pieces. A key thing just to state is that we can only update other people's state when we hear about it through gossip. Kind of makes sense. So we're going to update our own state data directly, then we'll pass it on with gossip messages, and we'll update others only when we hear from an update. How do we do that? Well, what would be the simplest possible thing we could do, given that we've got sigma, mu, so everyone else's data? We want to tell someone what's going to happen next. Like, how do we exchange data? Anyone, just the simplest thing you could possibly think of? Yeah, just send it. Send that dictionary across. Push. This is called a push gossip protocol. We literally just take that mu and we give it to the other side. Very simple. Any downsides to this?
Too much chance.
Yeah, way too much data, and it's mostly stale. We got no idea if that's actually new to the other person. So how do we improve that? We ask the other person for some indication of what they know so far. We call that the digest. Hopefully it's going to be smaller than that dictionary, or there wouldn't be much point. So how about we drop the values? We just return the version numbers. And then when we get that digest from the other side, we then give them the news based on that digest. So we're like, oh, I can see you have version 10. I've got version 23. Let me give you version 23. That sounds great. But since we're already talking, how can we make this better? Like at the moment, I ask for your digest. I give you my data. May as well you give me your digest as well. Pull push. The paper says this is the most efficient. I have no reason to disbelieve it. And we forget about those other directions for the rest of the paper. So those digests, like I said, just drop the values. So it's going to be the same kind of basic structure, but just a single version number for each of the key. That's the simplest possible digest. Cool. So even with that, we might have way too much data to send, right? So if we had 10,000 bits of news for another side, we're not going to send that in a single exchange because that could take arbitrary amounts of time. Again, we want to be able to keep the system flowing. We don't want arbitrary weights for network or CPU constraints. So we're going to have to build some kind of decentralized flow control. The algorithm, without any single points of failure, is going to have to make sure that we don't get stuck. And part of that is going to be defining an MTU. So like TCP, we're going to have a maximum transmission unit. That's just going to be defined as a number of tuples, which are the participant ID, the key, the value, and the version number. Now, again, to me, it's a weird thing that the paper doesn't worry about the size of the values, because obviously, if your values are like 4K videos, it doesn't really matter if you do a clever digest. That's going to take an arbitrary amount of time to send. But I think realistically, the gossip protocols are only going to be used for the kind of system where you're actually just sharing small amounts of information, where the values are probably not much bigger than the keys. metadata about a database, liveness information about another node, that kind of stuff. So that's my assumption why that isn't a super weird, gap in the paper.
There's no pieces of your MP3.
You're right. That would be another way of doing it, actually. Totally right. Yeah, fragment it up and then, yeah, that's true. That's true. Well, yeah. Nice. So if we have a limited size of exchange in a single gossip, we're going to have to prioritize, right? That's the other bit that we're going to have to use, decide on, and that gets straight into the next section, the reconciliation algorithms. So hopefully that gives you an idea of like the base problem we're trying to solve. Any questions so far about where we're at?
Versions are local to the node,
Yes.
right? And when the gossip's happening between the nodes, you trying to pull.
Mhm.
For 27, let me give you this, right?
Yeah.
If the versions are local, then how do you decide that? Or is it, at this point, is it still just chatter?
It's a great point. So the versions are local to a participant ID. So you know that you can like compare them within a single participant. So if we're both gossiping about Bob, we can compare the versions for Bob, but I can't in any way compare Bob's version 23 with my version 24. It would be a meaningless comparison. So that's what I mean when I say like the versions are local.
Oh, God, you still compare it with the version for the other. Okay.
Yes, exactly. Because we are gossiping about like that state dictionary that we know, and we know that node has controlled the version numbers. No one else is going to kind of assign them. And again, the important thing is there's no meaningful comparison between nodes of version numbers. Yeah, cool. No, great question. Other questions? Nice. Okay. So the reconciliation algorithm is going to be how we do that pull push. Like, what do we actually send? And again, we want to converge with probability one. That's like the important thing about anti-entropy. So the first, the status quo algorithm, the paper sets out to knock down is precise reconciliation. This is exactly what it sounds like. So we are going to send the digest we saw, and we're going to send exactly the data you need. Simple as that. Here it is in code. We got the digest from the other side. We look through every key of every participant we know about. We check if we have a higher version per key, per participant. You can see we don't do cross participant comparisons. If it's a high number, we include it. Super simple.
And they send the rest, right?
And then they'll do exactly the opposite. So like you can see we got PMU, Q, then we'd send our digest and Q would do the same thing. You get what I mean? So the other way around.
You don't need to send that, right? Because you send your stuff, you will know that the rest of the stuff is.
We do, so the pull push goes like, I ask you for your digests, you give me digests, I reply with stuff, and then you've also returned, or the other way around. We basically exchange digests and then exchange data, if you get what I mean.
Yeah, but what I'm saying is that I'm asking you for your digest, you give me digest.
Yeah.
And I give you the data.
Yeah.
And then you already know my digest if I gave you the data, because everything that I didn't give you, it's in you have to send me.
They have the same version of key or one of the keys. So you don't, the other one doesn't know which one of your keys is outdated.
It's actually, let's just have a look. I've got a kind of worked example we can have a look through. Cool. So this is just putting the code, maths logic. We'll just quickly talk about the ordering before we get to the worked example. So of course, again, we need to prioritize these exchanges. We're going to need some way of ordering them. Precise is very simple. We're either going to go for the newest or the oldest. We're going to need a clock for that. I actually don't know why we don't use the version numbers here. It's kind of interesting, but paper is convinced that we're going to do it by time and we need synchronized clocks. Don't know. But okay, let's have a look at a worked example. So if Q and P were gossiping, oh, sorry, this is actually going to be important. So for all of these examples, keep it simple. We're always going to be talking about the data of a single node. We're always going to be talking about R. So this is all replicated versions of R's data every time. But you can see we've got 3 nodes, so they all have a different view on R. Time is going to go left to right. So we're going to have different columns. We're going to see what everyone's view is on R's data at different steps. And like I say, for the gossiping, we only care about the version numbers. doesn't really matter what the values are for the gossip protocols. So which values are eligible for inclusion at time 2 between P and Q? So if P returns its digest, we've got 21, 20, 23, we're going to know that we need to send it, which ones? Yeah, exactly. The B and C are the only ones that are out of date relative. So we send exactly the precise differences. Kind of clear how we're going to make forward progress. Yeah. And with the push-pull, let's work it out. So I mean, in terms of if we get the digest from P, we got 2, 3, what are we going to missing? Yeah, I guess we don't have the inverse, right? So we haven't sent our digest. We
Okay. Already know that. So if you send the B and C, then you know that you didn't. Then I know that you didn't send me A, and therefore I'll send you A. Okay, maybe here it's because it's 21 in both cases. It's a bit of overkill. But
Yeah, the whole point of the paper is to just because it's constrained on the network and CPU.
It's actually a super good point, though. I can't like immediately verbalize why you need the double digest exchange. I don't think it's going to be massively important for the conversation to follow, but it's a very good point. I'll have a think about it after.
If you have a large number of keys, you won't be able to send, right?
Oh, that's actually completely true. Okay, so because we have the maximum transmission units, we are going to have to prioritize, and therefore there could be a big gap about the things we're going to be sending. That's a super good point. Thank you. Cool. Okay, so this works for sure, but the paper's authors claim that as we have a linear growth, as with the number of participants grow, because effectively, you know, the size of these gossip protocols is going to be like participants times keys, so it grows. It's going to require a lot of CPU and network. Now, you might claim that you could use a clever method to compute like more structured digests like Merkle trees, and people do. But again, they point out that takes a lot of CPU. And they point out that a bunch of these updates are going to be wasted because it's very, very common that you have a more recent version of a key, but you don't have the most recent version of the key. And whenever you share that, it's going to be needing to be reconciled again. And from their empirical kind of observation, it's about 2/3 of the time you're actually sharing data that has been superseded, but that the gossiper hasn't got it yet. So that's the kind of big gap they're trying to wipe out. And again, of course, the issue is that you're going to end up with availability issues and your gossip protocol is not so efficient. So here are the day enters, scuttlebutt. How are we going to solve these problems? I kind of crush this down to 2 key ideas. The first one is what we just said. Don't share stuff that you know is superseded and is going to have to be reconciled again. So you're just kind of avoiding any double work. And you're going to accept a slower kind of reconciliation propagation.
How would you know it's superseded?
You'll see. And secondly, make that digest tiny, absolutely tiny, way smaller than we have at the moment, where it kind of grows with the number of keys. We'll take out a whole factor of P times Q. We're going to drop the K factor from the growth. Cool. So the steps are, we're going to make a new rule, which I think you might have kind of assumed anyway. Whenever we update our state, we're going to pick a version number higher than anyone we used before. And that is effectively saying that we're going to have a unique set of version numbers for our keys, for our own Sigma map. That's very important.
Per key or across keys?
This is across keys. Yeah, across keys. So you basically just have a big integer that you just keep incrementing every time you update. And each person, again, no global ordering, just per participant. So we know that no 2 keys will ever have the same version. Very important. The digest is now just going to be the max that we know for each other participant. We'll see this all. Don't worry, we're going to do this in code as well, but this is just an idea. So it's going to get so much smaller. We've dropped an entire level of digest. So now it's just participant version number. Whereas precise, we had the key as well. And then this bit, I honestly think is easier to read in the maths than trying to verbalize, but we're only ever going to send a tuple when the version number is higher than the maximum version number that the other side has for that tuple. So we're going to forget about keys. That's the big important thing here. You can see that this, set notation, the set builder, we're ignoring the key in that comparison. So we're only comparing against the max known version for the other node. And this is the bit that took the longest to get my head around, and we're going to go through this. So don't worry, I'm not expecting you to get it from just that. This is what it looks like in code. So you can see the queue digest is much smaller, single level dictionary, no keys. We go through, we check that version number, and we're checking against the max. Okay. And then we do the sort, which we'll talk about in a bit, because we need to break it down a bit more. Any immediate questions? We'll do a worked example in a sec.
Maybe it's going to be covered later, but like we said, all of the peers. So like the version, the same version might point to different keys for different.
Yes, yeah, totally. Yeah, that's totally expected. So two different peers can have the same version numbers, not for the same. So in your moo map where it's like participant key version, you know, for a single participant map, you'll never have the same. But yes, absolutely, Alice and Bob can both have a version 10 in their map.
Mm-hmm. How can the version it's
that is the crux. Totally, we're gonna, yeah, that is exactly it. You're basically, because we know that we can never, you know, we're always going to have unique versions within a single participant. We can never reuse versions, and therefore, if I've got version 21, I will posit that you know that everything else has been outdated, and we'll see this soon. This is the bit that like blew my mind, because it's like, how does this work? How can this like drop so much information and still converge? So again, we're just looking at the data from R, so moo R. Here's the difference between Scuttle and Precise. If P and Q were to gossip now using Scuttle, what are they gonna exchange?
2, 3, and 12, 30.
No, they're gonna not exchange a single thing. There's nothing to exchange. That's the big difference between Precise and Scuttlebutt reconciliation, because the two maximum version numbers are the same. That's the big idea. So we're going to drop all of that other information, which is definitively new to P. You can see it's a way, way more recent version, but we're still going to drop it. We're not going to send it. Cool. So the big claim is that it's not designed to do that. We're not trying to eliminate everything. It's not precise. And it may seem like a shortcoming, but it's designed. We're trying to avoid that rework. And by the things we've said so far, we know that everything that we're leaving out is stale and will be needing to be reconciled again. And we can actually see that here, right? So we know if we have key 21 at the other side, and the other keys are 12 and 13, well, had either of those keys been updated first, we'd have got them first, because they've been lower. That makes sense. And again, this took me a zillion tries to kind of like fully be okay with, but that's the kind of basic idea. Cool. Okay, we'll dig in, don't worry. So I was like, I'm sure this is flawed. I'm sure I can figure out ways that this is not going to work. And is it possible that we're going to get into a situation where we don't reconcile something that actually doesn't need to be reconciled again? Be like the kind of contradiction for what they're saying. I'm going to do a worked example with more steps to try and create like weird gaps between version numbers and see where we get. Okay, so step one, I'm going to update just one version a bunch of times. So now they're not sequential. I found it a bit weird that all of them were sequential, kind of through my intuition. So now we've got 21, 23, 26. Okay. Now we're going to replicate with Q. And then we're going to update some more on R. So then we've got 30, 31, and 23. So we have like really interesting mix of versions now. Check my work here, make sure I haven't done anything that violates the constraints. But so the replication, oh, I should have.
Saying Q is asking R or R is asking Q?
I'm actually not asking anything right now, but that's actually my next step. So yes, now if we're going to do Q and P, what's the final state going to be? And also, sorry, I realized I didn't highlight, and I can't, but the top in the top right, we've also got 23, 21, which is also, valid. I posit. So let's say that now P and Q gossip, what's the final state going to be? Sorry, sorry, R and P gossip. I was trying to create a gap with R. So R, the bottom row, the origin, and P, the top row. They're going to gossip at this point. What's the final state going to be?
30, 31, 30.
Yeah, everything's fine. And try as I might, I couldn't find any problems with this. This does work. And it always fulfills, yep.
Like participant P, EC, that was probably a small typo because the update was only supposed to have happened in T6. There was no communication with P.
Yes, on T5 for P.
Yes.
Yes, sorry, I should have highlighted that one as well.
Okay.
Yeah, you're absolutely right. Cool. And so the invariance that's always going to be true, if you follow all these rules, is that we either have, so for process Q, either has the current mapping for a given key that's the same at the origin, or that it's been superseded. And that's the big idea behind Scala. This invariance always true. We're always going to make forward progress. Cool. Any doubts still? And it's totally reasonable to have doubts. Yeah.
The assumptions about the rate of updates on the ultimate owner node.
Does it make any assumptions about the rate of update on the ultimate originator, right? Yes. I think it kind of is. And to put this in another way, if we just see nodes going down as extremely slow updates, we could definitely get into a state where the node goes offline or just can only update incredibly slowly, which is almost the same thing for most kind of algorithms. We do end up with this situation where the node's gone, we're never going to get updates, never going to be reconciled again, and yet the gossip algorithm is not going to propagate that information. Which I'm not saying anything new here, this is just a corollary of what we've already agreed. So this is totally a thing. And one of the systems that I'll mention right at the end, I think calls this out as like a potential risk. That's a thing. So yeah, it absolutely does.
So is the question just time?
I don't think it is just time. I think it's literally just an integer, but it's, yeah.
Time, right?
Yeah, I guess.
When I update, I'll just up the time.
Yeah, I guess. I get the only thing is there's no assumption of like a global clock. And so I get a vector clock or whatever you want to call it. But yeah, that's, yeah, pretty much. And actually a lot of when we look at the experiments, they talk about staleness in seconds as well. So yeah, sure. Nice. Okay. So we talked about the digest and how we actually exchange data. How do we prioritize things? So this shouldn't really change the correctness too much, as long as there's some ordering guarantees that we never share, out of order version numbers. But we got two options here, breadth and depth, basically. Do we want to try and share information about as many participants as possible? Or do we want to share the kind of whoever's got the most news to kind of propagate? So scuttle breadth, we basically to go through all of the deltas that we calculate for our scuttle algorithm, and we just give them a rank. So the first one's rank 0, second one rank 1, etc. And then we just order by that. So we share everyone's first bit of news, then next bit of news, etc. Fitting as many as we can inside the NTU. Depth of the opposite. We look at the kind of stack of tuples we have per participant, and we call the participant with the most news to share participant 0. We give all of their news, and then if we've got any room, we give the next person's. Which is better? Well, I'm glad you asked, because now we're going to evaluate. So we're going to do a simulation with 128 nodes. They're all going to have one update per second. They're all going to have one gossip exchange per second. You can call it second, you can call it tick. I think tick is actually better for the simulation, but that's the idea. And we got 64 keys. We got an MTU, so maximum number of tuples to exchange of 100. And the scenario goes that at the start, there's no MTU, we're just trying to get everyone's state kind of equal, just so no weird nodes or anything cause a problem. We set the MTU to 100. We then double the update rate to kind of create some real stress on the system. So hopefully, now everything can be exchanged. We bring it down again, and then we set it to 0 and make sure that we converge. Because at the end, we should have no stale data at all, or we've failed as a gossip protocol because it didn't converge even with no new updates. And we're going to evaluate these algorithms with two, or at least for this experiment, with two metrics. First, the very, very stalest key. So of the entire system, what's the oldest key that hasn't been updated everywhere? And secondly, the number of keys that haven't been updated. And as you can see from this chart, scuttle depth is the best. Actually, you can't because the chart is absolutely unreadable and horrible. So I'll add this helpful arrow. But if you squint really, really hard, you can see that scuttle depth wins on both of these metrics, or does a pretty damn good job on B, and it certainly is winning on A. So we precise newest. You can't, again, it's going to be very hard to see, but take my word on it, the bottom line actually is precise newest. So it's doing very, very well on B. So the number of stale values, nukes them, great. But you can see it does extremely badly on the P99, like the very slowest couple of keys. It really sucks and really falls behind. So on the balance of the two, I think it's fair to say that scuttle depth is winning out, which is cool. One thing that is really interesting is that when I read the update rate, it was kind of weird that they're all the same, because that's not like any other system, right? You're always going to have some like noisy nodes, some slow nodes, all that stuff. So they actually used a zip distribution. So like, most frequent word or something. There's a big power law distribution. Some, like some people are doing most of the talking, lots and lots of people are quiet, etc. But apparently it doesn't make much difference. I haven't had time to check. However, something interesting happened when I read the Amazon presentation about this protocol. Can anyone spot the weird thing? Have a look at the results. Who's winning? Yeah. Precise newest, right? And again, this chart is really, really, really hard to see. So by the wonders of affine transforms, I compare them for you. And you can see precise newest is pancaking scuttle. Confusing, not explained in the presentation. So I thought, I'm just going to vibe code an experiment. So I've done this, tried to reproduce the paper, reproduced it all. And I think it's fair to say that this is like pretty much what they've got. So I have no idea what was going on with the Amazon presentation. I have no idea why they didn't mention that their own data seems to be contradicting, like that it's a better algorithm at all. I might even email them, see what they say. It's very intriguing. But yeah, when I reproduce the data, reproduce the experiment, you can see we get roughly the same shape. Everyone happy? And we can see that the loser is again precise newest, which also intuitively makes sense, right? I think I can see why it would be the one that has the worst kind of P99 behavior. It's just trying to do way too much work for the space. Therefore, it's going to fall behind. Kind of reasonable. Cool. Also, I'd really be interested if people to play around with this experiment. You can change all the parameters. I also added liveness, so you can kind of simulate things going down. So like half your nodes going down, coming back online, all that kind of stuff. Doesn't massively change the results that I can see, but I haven't had that much time to try. So are we done? Is gossip solved? Not quite. We still have the kind of classic overload issue that we could have some incredibly noisy nodes. We don't have any way to stop that dominating everyone else's time. So we might just end up spending most of the network's time replicating one pathological node that's just gone mad. What we're going to need is some, again, decentralized way to fairly figure out how much we should all be sharing, what we share, who we share about, all that kind of stuff. So again, got to be fair, got to stay decentralized, or we've completely broken the point of gossip protocols. We already have this brilliant way to communicate the gossip protocol. So why don't we try and figure out the update rate we should be sharing via gossip as well, is the idea of the paper. So each participant is going to have a look. How frequently am I getting updates? It's then when it gossips to someone else, it's going to say, hey, this is the update rate that I need. It's also got a max update rate, which we're going to adjust as a parameter soon. And we'll see how. And we are never going to change the constraint that the MTUs is the MTU. You're never going to send more tuples than the MTU. And so what we're going to do is when we gossip as part of that protocol, we're going to figure out how to apportion those combined maximum update rates and the desired update rates. And it's quite a lot of code. It's even it's incredibly simple in practice. Basically, if there's enough of both of us get what we want, we both get what we want, and we share any remainder. If one of us wants more and there's space for that, we'll do that. Otherwise, we'll just divide it by 2 if we can't come to a conclusion. Super simple, nothing complicated really. But the big open question would be, how do we change that max update rate? Like, that's the big thing. Like, okay, we know the update rates we want, and we know how to share them out, but like, how is that max update rate gonna come down if we just can't keep up? So the authors grabbed some ideas from TCP. If you know anything about TCP, you probably know how this is going to work, which is additive increase, multiplicative decrease, which is basically we're going to increase little by little, carefully, and if we go too much, we're going to come right back down really fast. And that kind of makes a lot of sense, because if you hit a certain point, you're going to create a back off, like a huge backlog. Everything's going to go terribly wrong. So that makes sense, right? Try and find the right point, come back down, keep coming, and you're going to fine tune it without any centralized control. And the algorithm is super simple. When we hit some consecutive number of exchanges where we fill the MTU, we're going to have to come back down. And conversely, when we hit a number of consecutive exchange, where we don't, we're going to inch up. And the parameters are simple as well. It's 3, so 3 is the magic number here. Like, if we get 3 bad ones, we come down. If we get 3 good ones, we go back up again. And that is it. Like, that is how the flow control algorithm works. And again, they didn't just kind of state that it worked. They went off and did some experiments. So the evaluation is basically going to cut the MTU way below what it was at the beginning. So we're going to make sure that we can go up from 0, because we're going to start off the max transmission per node at 0. Make sure we can go up, find the right rate, and then come back down again smoothly when we change, and then go back up again. So like, that's the idea. And so this is the experiment. Quiet time. They're actually kind of underspecified the quiet time, obviously. Honestly, when I was reading the paper, I was like, what exactly is going on here? But I've kind of reverse engineered it. I think they just put the maximum observed rate for each node at 0, and then they have to go up. Then we go MTU 100, and then we cut the global MTU, which wouldn't happen in production, right? Because that's a parameter, but it's simulating a network outage. So suddenly your network has gone to shit for some reason. And again, here are the charts. So we can see precise newness, again, making a really poor showing on maximum staleness. Honestly, it's the same flow control algorithm for all of these. So it's kind of not particularly expected that they'd have massively different update rates, as far as I can tell, unless I'm missing something. But anyhow, they, as you can see, mostly perform the same on a maximum update rate. And the paper claims scuttle depth provides the best trade-off between the two. Cool. Seems reasonable. Again, I replicated this just to see if I could get a similar result. I realize I've slightly got one screenshot that's out of date because it doesn't come from 0, but you can see, yeah, we've basically got a very similar shape, and we have a kind of similar loser anyway, which is the precise newest. Again, just has a very bad P99. Cool. Questions about the flow control? Sorry, I realized I went quite fast through the flow control bit. Yeah.
Does anything weird happen if the nodes have different MTUs?
Yeah.
You've got like hundreds of genes, you're slowly changing.
Yeah, it's actually a good question. I think maybe in that, you know what, I think it would work out. So the MTU is a local parameter, I guess. This isn't kind of specified in the paper, but the adaptation bit is local between the two nodes. I guess they might both have different views of what the fair result should be, but I guess the back off would still kind of apply, and the inverse, like moving up. So it's a super good question. Yeah, I have a hunch that it would be okay because of the fact that it's local adaptation, but I don't know for sure.
They copy TCP, then it's not expected to be the same width of the pipeline. Like if I have
Okay.
a connection with you, like my view of MTU of you and your view of MTU of me, different.
Mhm.
And if they copy TCP straight up, then it should work.
Makes sense. Makes sense to me. Cool.
Because it is not unreasonable to expect that if we have a connection, like the way I'm sending packets to you could be coming back in like a different path. There's no expectation that they come back in the same way in TCP.
Yeah, that's quite reasonable. And I guess like if I see more updates than you because I'm talking to more nodes somehow, we're like partitioned.
Yeah.
Yeah. Cool.
This any data for like scuttle breadth?
Absolutely great point. They basically just said scuttle breadth wasn't any good. So we were not going to bother showing it again in the final charts. Cool. So where's Scuttlebutt gone? Like the Cassandra paper, I think 2012 or something, quite a while ago. Is it still cutting edge? Are people still using it?
So in this case, unless I'm mistaken, your notion is random. You're trying to like randomly pick up here.
Yes. Yeah, it's always pick a pair random.
But that's not what Cassandra does.
Ah, interesting.
Cassandra doesn't do a random pair. It actually knows which one to send it.
Presumably the geometry of the
Like Cassandra,
network, it's important.
Yeah, makes tons of sense.
no, but in case of like a or whatever, you don't know who you're going to be connected with, so you have to do random stuff. Like let's say we are in a room and we have like different connections between each other. I don't know who I'm going to be connected right now, so I have an update. I'm going to send it to you. Hope that you would do that. In that case, I'm trying to send it, but that's not what Cassandra do it because it has a notion of a key hashed, and then I precisely know that if I have this, that needs to go to these three people, and I'm only going to send it to them. Otherwise, I'm not going to. And it works as long as you have half of the cluster up. So in that way, Scuttlebutt and Cassandra are very different. There is no randomness in that.
That's interesting. Is that, as I understand it's Cassandra, and I know nothing about Cassandra, by the way, but from what I've gleaned, it's just the metadata, node metadata that's shared by gossip.
Yeah, so
whereas like versus the actual data in the database.
Yeah, it's the only the metadata is shared, but it's also, I don't think there is any notion of randomness.
I mean, sure, you're right. I think like looking at the Cassandra code for Scuttlebutt, it's not like a one-to-one. There's definitely more. There's like a generation concept as well as the versions. It's got a lot more structure.
In Cassandra, the part that match this is the replication between the consistent replica of one node. So if you have one node, 10 replica of the data of that node, the scuttlebutt will be applied to the 10 nodes of the replicas, not the entire ring.
So you're saying that you Scuttlebutt to like replicate just the idea of the ring and the hashes, and then you just
Yes. So you only talk to the neighbors that they are on your ring, that they are the replica of your nodes. The rest doesn't matter. You can have a general view of the other nodes, but the metadata that needs to be replicated with your 10 replicas.
Yeah, I think you might be right. Needs to
So
be
there is the consistency number in Cassandra is the one dominating.
Yeah, you mean like the notion of like where does this, like if we have like 5 Cassandra nodes, do we all agree that this key needs to go to that node, sort of like replication before the data?
Yeah, there is one, there is the leader, and the other ones that they are the replica of the leader in terms of for that hash ring set.
Gotcha. I see what you mean.
Nice. So Scuttlebutt is still being used for new systems. So QuickWit is like an open source implementation of a database much like Elasticsearch. And if you have a look at the source code, they use ChitChat, this Rust library, just directly implements Scuttlebutt. Talking about like its influence on Cassandra. I think incorrectly saying the Cassandra borrowed gossip from DynamoDB in that DynamoDB doesn't, as I understand it, use Scuttlebutt. But anyway, you can it's still being used. The systems are very successful. So QuickWit got bought by Datadog, I think a couple of years back. So still very much in play. That is it. Here are some extra things you might want to read. So Cassandra source code, you can actually see like some of these algorithms implemented and like elaborated. It's not just like straight scuttlebutt. Secure scuttlebutt, the weird and wonderful social network thing I mentioned, quick quit, and play around with the admittedly vibe coded re-implementation of the experiment. You can change all the parameters, hopefully, make it a little bit more realistic with node outages, all that stuff. Yeah. Cool. What do we do? Go to pub. Oh yeah, sorry. More questions. Yeah.
What is the secure scuttle?
Yeah, so like I say, it's like a platform for building secure distributed systems, like particularly for, I guess, anything where you want the data to stay secure. So it's like
The sense of Byzantine participant.
I guess, I don't know, but certainly like encrypted is the idea. And that, at least for me, maybe bounce off it as a social network because you had to download like gigabytes of data. It was like running a node of a blockchain or something. It wasn't super practical, but kind of cool.
I believe the person who invented second Albert now works for Blue Sky.
Ah, that makes sense.
I don't think his IT has died. I think he's like, I tried this for 10 years, that didn't work. So I'm gonna do it in like a different way. But I think a lot of those team and IT has just ended up in Blue Sky.
That's super cool.
Very different way.
I think earlier. So is the idea here that the ultimate owner node of a dictionary, its key value pairs, will be on a continual basis for some period, emitting gossip about itself, even if the values have not changed.
Yes, yeah, because of this like random pick for gossiping, it doesn't like, there's no sense of like, oh, I haven't heard any news from you for ages, I'm going to drop you from, talking to you. So yeah, you will eventually and end up gossiping again. And I guess that's how the self-healing works. Like even if you've never heard about them before or they went offline for a bunch of time, you're still eventually going to gossip with them or someone who's gossiped with them more recently than you. All good. Yep.
Go back to like one of those tables slides.
Yeah, roughly when?
We had like a T5.
Yeah, sure. Let me have a look. This one or?
No, the one with 34 and T5.
Ah, yeah, cool. Okay.
So again, like, not really this example, but I was thinking, and I'm probably missing something obvious, but we said that the version,
Mhm.
it's specific for like every participant, right?
Yes, version numbers not comparable across participants. Yeah.
But also every participant will receive updates on the keys. Or only.
Yeah, so everyone can hear about everyone's state eventually.
Yeah, so pretending that we are at the issue, so not yet at T3.
Yeah, cool.
Like that would be, for example, that P receives 4 updates. So
Yep.
maybe all of them on the key B. So it's going to have key B or to set to 22, 23, 24.
It could, yeah, sure. It could only get updates that were higher than 21, right? So it could only get version 22 or 23. In fact, it could only get version 22.
Yes, but
Yeah.
then it gets another update, and then another one is going to be 24.
Yes, yeah, sure.
And then independently,
Mhm.
because they haven't gossiped with each other yet,
Yeah.
participants are called out to receive an update for another key that could be like C. And
Well, participant R is the originator for R, right? We're only talking about R's data here.
oh, okay. That's where I was confused.
No, it is confusing. Like, honestly, it took me the longest time to like completely convince myself of how this works. So good question.
I still haven't wrapped my head around that. Now that I know how I got it wrong, and I can go back to it later, maybe.
Awesome. Other questions? All right. Well, thanks for being a great audience. That was some really good questions. Cheers.